Hey, on today's episode of On.net, we're going to be looking at using dotnet-dump to debug memory leaks in Kubernetes. Come and check it out. Welcome to another episode of the On.net show. Today we're going to be talking with Mike again about debugging memory leaks in .NET apps. Mike, thanks for being on the show again. How about you quickly reintroduce yourself?
Absolutely. Thanks, Rich. So my name's Mike Rousos. I'm a software engineer on the .NET customer engagement team. We go out, help customers get started with new .NET offerings and other Azure app development things and make sure they're successful. And we bring all those learnings back to make the products better.
Awesome. So let's talk about what memory leaks even are and why
Sure.
we have them.
Yeah, absolutely. So a memory leak, just generally speaking, is any time that you've got memory allocated in your app that is long-lived and takes up a lot of space, such that eventually you run out of memory. And they come up a lot of different ways. A lot of people don't think about memory leaks maybe when they think about managed code, because we have the garbage collector that should go in and clean everything up for you. But you still can run out of memory in .NET, of course, if you have things either that the GC doesn't know about or that the GC can't clean up because they're still referenced. The way this typically happens in .NET code is you'll have some sort of static object, or you'll have an object that's owned by a long-lived thread that grows and grows and never is able to be cleaned up because there's always some sort of reference to it. One place where you might see this, for example, in the example we'll look at in a little bit here would be like if you've got some sort of cache of objects that you're remembering and it keeps growing, but you don't have any logic to get rid of it. The other way this could happen would be if you had native code that was holding on to memory, which the garbage collector isn't going to know about. So if some component has used like the Marshall class to allocate memory, or if you're interoping to native code and it allocates something, the garbage collector doesn't have any knowledge of that. And so now it's up to that code to dispose it. I've seen issues before where code wasn't disposing properly, and so the cleanup code wasn't running, and stuff was just hanging around, allocated in native code indefinitely. It's like those are the sorts of things we're looking for.
Makes sense. And I guess some of it, I hesitate to use this term, but it might break out into like unintentional and intentional.
Yeah, that's true.
Because obviously no one creates memory leaks intentionally.
No.
But like some of these are the unintentional ones where it's like, yeah, the dispose logic wasn't quite correct, and I did something incorrect and accidental. But other ones are, well, your code is just growing this cache forever.
Yeah.
Like you have this dictionary,
Yep.
and you just constantly add things to it, and you clearly never thought about removing it. So in that sense, it's intentional.
Right. Yes, exactly.
Yeah, and I guess you probably see both categories with.
We do. I actually think the intentional ones come up more often when I'm working with customers, because people will think, oh yeah, we're just going to store it. Because the thing is, there's always this trade-off between memory usage and sort of throughput. And so people a lot of times will say, hey, well, we're gonna keep this in memory so that we don't have to recalculate it, we don't have to retrieve it again. But if you're not careful, then you end up running into the opposite problem where, okay, well, things are going really fast until they stop. And so that's probably the one that comes up more often. But you do see both. You see situations where someone just forgot to clean something up, and you hit that as well.
Also, before we kind of dive deep, would you say that the move to the cloud kind of changes the game here? Like I remember back in the day, both at Microsoft and also with the customers that we would talk to, you talk about like, we're going to procure this server and it's going to have, umpteen gigabytes of memory, and so everything will be awesome. But in the cloud, that where you're paying for every aspect of the machine that you're using on like regular basis every minute, presumably people have more sensitivity to these large caches.
They do. It's definitely more of an issue. Like you said, it used to be If this app was crashing after running for a week, like, well, double the RAM in the machine. Now it lasts 2 weeks. Like that solution doesn't work when you're in the cloud because people are very sensitive because that RAM is money. Especially when you start talking about containerized solutions, it's common to want to pack a lot of containers onto one host. So you put a resource limits in place to say this container can't use more than a gig of memory or 500 megabytes of memory or less. And so you very quickly notice when you're leaking things in that case. Even the runtime has had fixes to better handle resource limits. I know we did some work in the .NET Core 3 timeframe so that the runtime itself would be more aware of those sorts of things. So .NET does it now, but customers' apps need to be aware as well that they may be running in very limited environments.
Yep, I know. I wrote the spec for that one.
Oh, there you go.
Yeah, so, okay, so how about you get us now into the details now that we've captured the scope, but like the topic. Show us what you got.
So absolutely. What I thought we'd do today, I mean, it's a huge topic, so I thought the best way to do this would just be to go through a demo and just say, hey, let's take one example, let's debug through it, showing how some of our diagnostics tools help here, and just kind of give an example. This one's going to be a leak in managed code. If we want to look at native, it's a little bit different, as a different pattern of debugging. We could do that in the future. But for this one, we're just going to take a simple example I coded up where you mentioned a dictionary. That's exactly what I've got. I've got a dictionary, which I am not using very wisely, and it's going to cause problems. So if we can go ahead and share my screen, I'll jump in and sort of demo this. So again, I tossed the demo into a Kubernetes cluster just because, why not? It can sort of showcase how we can use these tools cross-platform, and that all works fine. So the thing I'll start with is I'm going to figure out where my pod is. I'm going to exec into that. We did some diagnostics previously on this show, and one of the tools that I highlighted was .NET counters. And we're going to use that again because it's, again, very helpful for understanding what's going on at a high level in your .NET app. So we're going to start in the exact same place. We're going to be using .NET counters to monitor our app while we apply a load. In this case, the scenario that we're looking at is this app works fine up until a point where all of a sudden users who are hitting its endpoints start getting errors. And eventually you have to just sort of like restart the pod to solve that. And so we're going to take a look at that and see if we can figure out why we're getting those failures. So we've got our app here. We're going to go ahead and install .NET counters. This is a brand new container. It just got deployed, so it actually doesn't even have curl on it. So I'm going to very quickly just do an apt-get install curl. You could use wget, whatever you want. The point is you need some way of making an HTTP request to download our tools. We talked previously about how the .NET CLI diagnostics tools are really easy to use now because you just download them from the internet and they're ready to go. So we're going to do that here. Go out to aka.ms/ I'm going to check my notes, make sure I get it right, but it's pretty simple. It's .NET counters and then the runtime identifier. So in this case, Linux x64, because that's the OS we're running under. Oh, I have to also provide the output file name, so we're going to download it to .NET counters. Right, that's done. So we're going to make that executable. And so with that, we are now ready to run .NET counters. We can do PS to list all the processes, but in a container, you're going to typically be profiling process number 1. So we'll monitor process 1. Just a minute to start up. All right. Oh, so my nice big font has got things kind of lined up funny here, but I'll sort of translate it for you. So right now, there's not a lot happening. You can see thread pool count 0, nothing's in the queue. This is going to be our working set, even though it gets cut off. Working set is 82 megabytes. And if we look at our managed heap size, it's up here. It's small as well. So yeah, that's not the best view, but we'll go with it. It's good enough. We're only going to be in .NET counters for a minute. What I'm going to do is I'm going to use Siege to run 50 concurrent users just for a minute, hitting this endpoint. It's the worker/run task endpoint. It's going to do a little bit of work. And what we're going to do is we're going to, while this runs, we'll watch to see what's going on in our .NET process. Previously, when we were talking about thread pool exhaustion on a previous video, we noticed that the thread pool count was going up a lot. Here we notice it's staying in the single digits. We still have, you know, stuff in the queue because we have 50 concurrent users. So that's to be expected, but the thread pool themselves is fine. But the working set is going up here, and it's mostly monotonically going up. There's a few places where it gets smaller a bit, but what you would prefer to see would be it staying level, or maybe going up, coming down. In this case, it's going up, it's not coming down. I also noticed that the GC heap size, which is this one, if this was all on one line, you'd see this was the size of the managed heap, is a similar number, which also is very large. So what this tells me is that we're using a lot of memory. Doesn't necessarily mean there's a leak, but it means that a lot of memory is being used. And in this case, the memory is being used by managed objects because the GC heap size is similar to the working set. If this was a native leak, we'd see a very large working set relative to a smaller heap size. The other thing that we notice here after we run it, the transaction rate seems okay, I guess. I don't really know what we're expecting here. But we've got failed transactions. We only had about 92, 93% of our requests come back with a 200. So that's problematic. So the fact that some of our requests are failing makes me also want to go look at logs. I talked about how .NET counters is a really useful place to start when you're diagnosing a performance or reliability problem with .NET. The other place that you want to start is your logs. So look at any sort of monitoring solution you have in place, like application insights. Look at logs that are just going to console standard out. Because a lot of times when requests are failing, you'll be getting errors, warnings, something like that in your diagnostics. And it's going to sort of be a clue as to what's happening. So in this case, we've noted that a lot of memory is being used, a lot of managed memory is being used. And to sort of take the next step, I'm actually going to hop out of the Kubernetes pod for a minute, and I'm going to use kube control logs to look at the logs we're getting from that container to see if there's any clues there. So we see a lot of successful requests, and then all of a sudden we're getting some red here towards the end. So if I scroll up and look at one of these failed requests, we're getting an out of memory exception. So already we've got a clue. We were trying to allocate some memory. We weren't able to. The request failed. And already this is enough where we could start looking at this call stack to see where this memory is being allocated. It doesn't mean that this is the place that's leaking, but the fact that it's trying to get memory means there's a chance it is, and so it's worth looking at. But at the very least, we see an out of memory exception, which is unexpected. And we saw a lot of memory being used relative to what we expect to be used. And I say relative because if I look at my Kubernetes manifest that I used to deploy this, I'm limiting the amount of memory that can be used to about 2 gigabytes. And we were approaching that in our working set. So it's not a ton of memory for some applications, but in this case, I'm not expecting this web app to be very large. So that's getting towards the higher end. The out of memory exception, though, is unexpected because what should be happening, even if a lot of memory is in use, is that the garbage collector should be going in, cleaning things up when we see memory pressure, make room for more allocations, and that's obviously not happening. So we've got a situation here where the garbage collector isn't able to clean up, and so we want to figure out why.
So clarifying question, which is normally I would think with an out of memory exception that we'd be looking at process teardown, but
yes.
But these requests seem to keep on going and they have legit stack traces. So can you speak to that?
You know, I'm not sure. I don't know, because you do usually see the process get torn down, and then you sort of have to look at logs from the torn down process to get anything. And a lot of times with an out of memory, sometimes you don't. It's sort of like a Stack Overflow. You may or may not have a stack. A lot of times you don't. So I'm not sure what the difference is. Do you happen to know, Rich? I know you work in this space as well.
Yeah, I was actually super surprised to see that because I thought with so maybe that's now that this is a little embarrassing, but like so Stack Overflow is definitely a fatal
that one just dies.
I thought out of memory exception was in the same category, but maybe that's
I think it often is. It may depend how the memory is being allocated. In this case, just to kind of skip ahead here, if I look at what's going on, where are we? We're in what are we doing? Yeah, I don't see anything obvious going on at
Well,
that
we don't need to belabor this point. It was just
Anyhow,
something that popped out to
something to
me.
follow up on, but yeah, it's a good question. I actually wondered that as well, and I will tell you that I've run this demo a few times to sort of prep, and I'd say about 90% of the time it fails like this, and about 10% of the time the process tears down. And so my theory is that it depends what sort of allocation was happening and whether the runtime's able to catch that or not. There are certainly cases where you can't. You're correct.
Well, we'll ask Maoni after the show.
Yeah, Mahoney can educate us, and we'll we'll give an update. Anyhow, the point is we are seeing the out of memory, and we saw some high memory usage, so we sort of have some clues of what's going on. As far as next steps go, this is another place where dotnet-dump is useful because when we were talking about some of the other performance issues in the past, we were grabbing a dump and we were looking at the threads and what was on the call stack. In this case, dotnet-dump also will collect a dump that includes heap information. So it's going to have information on all of the objects that are on the managed heap. And so one good way to learn more about this sort of situation is to capture a dump and then take a look and see what's there using the memory. And beyond just capturing a dump, because that can be a little bit tricky when you've got a lot of stuff there and you're not sure what's maybe new or what's expected to be there versus what's just sort of hanging around when it shouldn't. A good tip is you can collect multiple dumps over time, and then you can use Visual Studio to diff those heaps and find out what's changed. So if I take one dump, early in the process, then I let the memory grow on in that case where I'm not expecting it to, and then I grab another snapshot, I can diff those, and it'll make it more obvious. Okay, here's this memory that, yeah, it's taking up a couple hundred megs, but it's just always there. That's not interesting. It's the stuff that's sort of accumulating that's really interesting. And in this case, my container's in a bad state where it's basically out of memory, so I'm going to recycle that container real fast, and then we're going to do the same applying of load again. This time we're going to capture a couple dumps and we're going to take a look at them. So I will get rid of that deployment, and I will redeploy it just as a quick way of tearing down the container and standing it back up.
Yeah, here you're kind of just proving one of the benefits of containers.
Yeah, right, because there we go. It's standing up again, and it's all ready to go, brand new. So yeah, makes it easy. I mean, if this was on a server, you'd kill the process, restart it, but it makes it so easy to do when it's in Kubernetes like this. So once again, I'll hop in there, and we'll this time, instead of installing .NET counters, I'm going to go through that same exercise, but I'm going to install .NET-dump. It occurs to me I should have had curl already installed in my container image. That would have saved us a minute here, but it installs pretty quickly. So
pro tip, you on recent Debian and Ubuntu versions, you don't need to type the -get.
Just there you go.
By itself.
Just apt install.
Yeah, that's the new way.
I will try that then.
Yeah.
Cool. All right, so let's go ahead, and I mean, we don't really need a different folder, but it doesn't hurt to just keep things organized. And then we'll pull down, in this case, it's going to be .NET-dump. And here. Okay. So now what we'll do is we'll do the .NET-dump, collect, and we give the process ID. So I'll go ahead and kick this off again. So sort of early on in this process, I'm going to run this. It's going to capture a dump, and I'm going to wait a little bit. In this case, I've got it rigged up to allocate memory very quickly, so we don't have to wait long. In the real world, you might wait a little longer so that you could sort of see that heap growing. But we'll capture a second one so that we can tell the difference. And this one takes a little longer because there's more to write, because when we're doing this, .NET-dump has some options where you can choose the sort of dump you're capturing. If I look at the help for the collect command, you can see you can do heap dump, mini dump, full dump. By default, we get the full dump, which is going to be everything that's you know, the heap, the stacks. Typically, that's what you want. If you're concerned about how large the dump files are, you could do like a mini dump or a heap dump and they'd be smaller. In this case, though, we do need the heap information, so mini wouldn't work. But you can't specify. In this case, I'm just doing the full dump, so they're going to be large, and that's not really a concern. You can see, you know, the first one was like 720 megs. The next one was almost double that, just because it includes all of that information of what's sitting on the managed heap. So as before, then, I'm going to pull these over to my Windows Dev machine because you can look at these in Visual Studio, even though they were captured on a Linux container, which is really nice. It's a cool feature of VS. But as before, I'm also not going to copy them live because I don't know if copying 2 gigs would kill our stream here. So I'm just going to instead go to sort of where I've already got dumps that I copied earlier today that are the same. Let's see, scenario 2. I've got the same dumps here. I renamed them to Managed Leak 1 and Managed Leak 2. The Managed Leak 2, of course, being the one that was taken a little bit later. I also have in this file, I copied the apps PDB out of the container as well, just using a kube control copy, because it's useful so that we can have the symbols for our app and know what line number things are happening on. And then I also use .NET symbol to download the debugging files and the .NET host for one of these dumps as well, because that way we're sure to have the right files to open these up on a machine which isn't the one where we captured the dumps. In this case, it says they already exist. That's fine. So we've got our dumps. Let's go ahead and take a look at them. So I'm going to open up Visual Studio and we'll check it out. Like I said, this is going to be similar to what we did last time. And the text is probably going to be a little small here because I don't know of a good way to zoom in Visual Studio outside of just changing the font of the editor, which is not what we're doing, but we won't be in here too long. So I'll sort of explain what we're looking at and we'll go from there. So when we open up the dump file, previously in the other video that we did a few weeks ago, we did debug with managed only to sort of jump in, look at the different threads and what was going on. This time I'm going to use debug managed memory, and that's going to give us that heap view. So I'll open that up. All right. So then what we've got here is it is showing us all of the objects on the managed heap. Now you've got a couple filters you can play with. A lot of times just my code will be enabled by default. I find sometimes this is useful, sometimes it's not, sometimes it hides stuff I want to see. So kind of play around with both ways. Same things with collapse small object types. This will take any objects that take up only a very small portion of the heap, and it will just lump them in with whatever object is holding on to their reference. And so this is a way of sort of focusing just on particular large objects. And again, you can sort of turn that off or on, see what happens. In this case, because this is a contrived scenario, I mean, just sort of glancing at this, we can immediately see that there's tons of memory being used by byte arrays. But in some cases, it might not be so obvious. So what we can do is in this compare to menu here, I can select a baseline and I can choose managed leak 1 as my baseline. And this is where we're going to get that diff between two different two different dump files, and we'll be able to compare the heap. And so we actually now get columns for size diff and inclusive size diff. The difference between size and inclusive size is just size is how much memory is being used for this particular type of object on the heap, whereas inclusive size is both the size of objects of this type as well as objects that they're holding on references to, so all of their children objects as well. But here now, in addition to just the size, we also have the diff, which is useful because there are some objects like, let's see if I can find an example, like string. You know, we've got 200K of strings, which isn't a lot, but you can imagine, a lot of times there's many strings in a process, but you can see that the number of strings didn't change. In fact, we have less memory being used on strings than we did in the first one. So that's probably uninteresting. We're not leaking strings. So what I'll do is I'll sort this by size, diff, and bytes. And the very obvious culprit here is these byte arrays. We've got 300 megabytes more byte arrays in the second dump than in the first one. And the total is up over 500 meg. So even in the first one, there were already a lot. So from here, you can click this view instances little icon that shows up to see, okay, we know that we've got 5,000 byte arrays, but what are those byte arrays? So in here, it's going to list all of those instances, and you can even right click and add to your watch window. So now if I come down here and look at my watch window, well, here's the byte array. In this case, that's not super useful because it's just a bunch of random bytes, but it's pretty common in scenarios I've helped customers through to have strings in the heap, possibly even being the thing that's leaking. You come here, you can look at that string and you can get a clue about where it's coming from. You might recognize, oh, the contents of this string look like a response that we get back from some dependency that we make an HTTP request to. Or, oh, this string is this file that we were loading from disk. Why is this still hanging around? Or whatever. In this case, it's just a bunch of random bytes, though it's exactly 100K random bytes, which might be a clue. But okay, that's what we've got there. The other thing we can look at in this view where you can look at these different types of objects is we have the paths to root view, which shows why this object is still around and hasn't been cleaned up. Like what's holding the references to it. And you can sort of walk up these trees until you get to a GC root, so you understand why this thing hasn't been cleaned up. So in this case, we walk up a little bit, and I know the font's small here, but we see there's one instance of a concurrent dictionary of GUIDs and byte arrays that's holding the reference to all 5,000 byte arrays. And so there's something on it, and it's labeled local variable. So Visual Studio is telling us that in our app, we have a local variable. It's not a static in this case, so it's on some sort of long-running thread. But we've got a local variable that's a concurrent dictionary that has just a ton of large byte arrays in it, and that's why we're out of memory. Now, typically, Visual Studio would also show you which type this concurrent dictionary is owned by. But in this case, I think we're actually running into a bug. I sent this dump over to the VS folks earlier in the week when I was kind of prepping this content, and they confirmed that this is a bug. It should be showing that, but it's not. So they're going to be getting that fixed. But I think it's okay because actually is an opportunity for us to show some other ways that you can look at these heaps, which are pretty easy if you don't want all of the features of Visual Studio. And it also helps because I know this is super small on the screen. One of the other things you can do is you can take the same dump and you can open it using a number of other debuggers. You could use something like WinDBG. On Linux, you could use LLDB, or you can use dotnet-dump itself to analyze the dumps that dotnet-dump captured. So I'm going to show that real quick because that's going to let us track even farther back what's holding on to all of these byte arrays that have become problematic. So what I'm going to do is, I could do this on my dev machine, but because I'm doing it with the dotnet-dump tool on the command line, one of the really cool things about that is I can do it right in the Linux environment if I want to. So if you're debugging something, you capture a dump in your Linux environment. If you just need to check something quick and you don't need all of the power of Visual Studio, you can just use dotnet-dump right there to crack open the dump and see what you need. So I'm going to connect to my pod again. I'm going to jump back over into that tools folder. And then from here, we can run dotnet-dump, but instead of doing the collect command, we're going to do dotnet-dump analyze, and we're going to pick that dump file. And now we've opened up the dump file using dotnet-dump in my Linux container, and we can use SOS commands to debug it. So like, for example, CLR stack will show us the stack of the current thread that we're on, which in this case is uninteresting, but it's a quick way to make sure that debugging's working. If you're not familiar with SOS commands, SOS is a set of extensions that allow you to debug managed code. And if you go out to the docs for dotnet-dump on docs.microsoft.com, we've got a real nice list of all of the SOS commands that are going to be useful. You also can type help inside of dotnet-dump analyze, and we'll list them all there as well, so you can familiarize yourself with what the different options are for when you're debugging on the command line with SOS. In this case, we know that our heap has grown large, so we might start with a e-heap-gc to look at the GC heaps and get information on them. So we get information on where the Gen 0, 1, and 2 heaps are. We get information on how large they are. We get the large object heap. Again, I've got a lot of wrapping going on in this window, so it's kind of hard to read this table. But I'll sort of direct you to the large object heap is quite large in this case. We've got allocated size and committed size. compared to just the ephemeral heaps, which are small. So this tells me that the thing that's leaking is probably large objects. Now, there's no reason that you couldn't have a memory leak with small objects also. It just so happens in this case that the objects that are leaking are big. If they're on the large object heap, they're over 80K. And so that kind of helps narrow down what we're looking for. The other command that's going to be super helpful here is dump heap -stat. Dump heap is a command that shows you all of the objects on the managed heap. Now, in this case, we've got a gigabyte worth of heap, so we don't want to see everything. But if we do -stat, it's going to sort them by type, and we're going to get a summarized view of the stats for all of the different types of objects that are on the heap, sorted by how much space they're using. So if we come down at the bottom here, we can see the very clear outlier of byte arrays, which are taking up just a ton of space compared to anything else. And so now we know that byte arrays are interesting. We've got, here's the ID for the method table for the byte array type. And then here's just like a count of objects and a size. So what we can do with this is we can grab this. And also the size and the numbers don't line up because this isn't the same dump I was debugging before. This is the dump that we just captured live on the show. The other one was the one that I captured previously that I didn't bother copying out of my Kubernetes cluster. But what we can do now, we know that byte arrays are interesting, so let's go ahead and rerun dump heap. But this time, instead of summarizing things with -stat, we're going to use -mt to only list objects for a certain method table. So we're going to only look at objects on the heap that are of type byte array. So this is going to list all of our byte arrays, and there's lots of them, of course. You saw how many there were. But we can now look at these and we say, okay, we can start picking some of these and understanding what they are, where they come from. So, you know, we could take one of these and we could do dump array. We're not going to look at everything, but, you know, maybe the first 10 objects of this array. We say, okay, here we go. And of course, the location is just a few bytes after the array itself. So we got a little header information, but I could grab this, and .NET-dump allows you to sort of inspect the memory there. So we could do a DB. Maybe we'll look at 1,000 bytes worth of information at this address. Okay, here's the bytes. So again, it's wrapped, but you would get sort of like the ASCII representation here. So if this was a string or something, you could see what it was. In this case, it's random bytes. It's not super interesting. What is really valuable for this scenario is the gcroot command. Gcroot allows you to specify an object. So in this case, we're going to give it this array. And it's going to tell us the roots of what's referencing this object. So again, we've got our byte array. And if we start walking up this list of gcroots, you can see that the byte array is held onto by that concurrent dictionary. Remember, here's the concurrent dictionary's node. Here's the concurrent dictionary itself. But this one actually doesn't have that same bug, so we're able to keep going. And we can see that the concurrent dictionary that VS called a local variable belongs to a type called profile picture cache bad, which is a suspicious name. Usually you don't get such red flags. But this bad profile picture cache object is in an object array, which is being held on to by our app's dependency injection container types. So what we can start to piece together here is now we have an idea what that long running thread was that was holding this. This is something that's in our DI container. So somewhere in our DI container, there's a collection of objects. Amongst them is something of type profile picture cache bad, which has a single concurrent dictionary, which has thousands of byte arrays in it that have used up all our memory. So at this point, we know enough. We can come over into our app. We go into profile picture cache bad. Sure enough, it has a concurrent dictionary, and when we cache something, all we're doing is we are trying to get it from the dictionary. If it doesn't exist, we add it. So when we have a lot of users looking up a lot of different profile pictures, eventually we're going to start adding more and more to this dictionary. It's going to grow and grow, and just like we were talking at the beginning of the show, you end up with this huge object that's never being cleaned up. If we look in our startup class, you can see that we are registering that cache as a singleton. So it just got the one instance, and it just lives forever and grows huge. I also have here profile picture cache good. I have a different endpoint on this API that does this in a way that's not going to cause problems. And what we do there is we use iMemory cache out of the Microsoft Extensions caching memory package. And this is a cache that works very similarly to just having a concurrent dictionary, but it also gives you the ability to set size limits and expiration times. So I'm able to set this up so that now I'm able to add something to the cache. I specify how large it is because when I set up my cache, I can say this should never be more than, in this case, I'm saying 100 megabytes because I'm saying that here size can be measured in bytes. You can determine that yourself. So we say this cache is never going to go larger than a certain size, otherwise things will get evicted from it, and things won't live in the cache longer than 5 minutes. After 5 minutes, they're going to be marked as expired, and so if we need to, we can clean them up to recover some memory. So if we were to rerun this, I know this is probably, we're getting short on time. If we want, we can rerun it. What you're going to find is that we get much better performance here. We don't run out of memory. And this is kind of the way we wanted to do it. But really what I wanted to highlight was the diagnostics tools we're able to use to get to this point, to figure this out.
That looked awesome. I loved the power of the tool you showed us, dotnet-dump.
Yeah, it can do a lot.
Yeah, and obviously there's a bit of a learning curve.
There is.
But like the fact that it was able to show you those GC roots in a way that very much aligns with your source code. I mean, it was basically kind of like a stack trace, even though
it feels very similar.
Yeah, and right, once you saw that, it was like, okay, it's super obvious what's going on.
Yeah.
So awesome, and all cross-platform.
It is, yeah, exactly. This just works. If you could SSH into the machine, you can run dotnet-dump and you can do all your analysis.
Or Docker exec.
Or Docker exec. That's right.
Yeah.
Yeah.
Awesome. Well, this was another great kind of addition on the diagnostics journey that you've been taking us on.
Awesome. Yeah. Hopefully it's helpful.
I think it will definitely be helpful for people.
Good.
Their examples, though, are probably not going to be quite as contrived.
They're not going to have a gigabyte of byte arrays and nothing else on the heap. But hopefully the same techniques will work. It'll just take them longer than 10 minutes to figure out. They'll spend an hour on it instead of 10 minutes. But these are the same things we do with customers who have actual issues with their production environments, and we're able to make progress. So I feel pretty confident that customers will be able to get to the root of their problems.
Totally. Okay, well, thanks again for being on another episode of the On.net show. And and I hope everyone who watched this enjoyed the show. Thanks, Mike.
Thanks, Rich.